Welcome to the Quiet Explainer. Today, we ask a simple question. Does space ever end? You do not need a physics degree. You do not need to take notes. You can simply listen. If your mind wanders, that is fine. If you miss a detail, that is fine. For the next 2 hours, we will move slowly, step by step, from what we can see to what we can only imagine. If you value calm, structured explanations like this, you can subscribe. It helps the channel grow. Now, let us begin at the edge of what we know. Look up at the night sky. Not with urgency, just with quiet attention. At first, you see darkness, a wide, deep darkness. Then, slowly, points of light appear, small, steady, scattered. These points are stars, very far away stars. They look close together, but they are not. Each one sits at a different distance. Some are dozens of light years away. Some are hundreds. The sky does not show depth easily. It looks flat, like a dark canvas with lights pressed into it. This flatness is an illusion. Your eyes compress distance. The stars are not attached to a surface. They are suspended in vast three-dimensional space. When you look up, you are looking outward, not upward in a simple sense. Outward into distance. Some nights, the moon is present, bright, clear, close compared to the stars. The moon is about 400,000 kilometers away. In cosmic terms, that is nearby. The stars are incomparably farther. If you stay still long enough, you may notice patterns, shapes formed by connecting bright stars. These are constellations. Human inventions. Ancient cultures trace stories between these points of light. Hunters, animals, heroes. The stars themselves are not arranged to form pictures. We arrange them in our minds. This is how humans first made sense of the sky. For most of history, people believed the sky was a dome, a curved ceiling above the earth. The stars were thought to be fixed to that dome, moving together each night. The sun rose. The sun set. The stars turned overhead. Everything appeared to circle us. This feeling is natural. You stand still. The sky moves. It feels central. But this, too, is an illusion. The earth is rotating. Slowly, steadily. Once every 24 hours. The motion of the stars across the sky is the motion of our planet. The night sky changes with location. Travel north. The patterns shift. Travel south. New stars appear. The sky is not the same everywhere. It also changes with time. Different seasons reveal different constellations. This happens because Earth moves around the Sunday. So even the familiar sky is dynamic. If you leave city lights behind, the sky deepens. More stars emerge. A faint band of light stretches across the darkness. This band is the Milky Way. It looks like mist or distant fog. It is neither. It is the combined light of billions of distant stars. Too many to distinguish individually. When you see the Milky Way, you are looking along the plane of our galaxy. You are inside it, looking across it. This idea can rest gently in the mind. We are not outside observers. We are participants within the scene. Some points of light move differently. They wander slowly over weeks. These are planets, closer than the stars. Their motion once confused early observers. Now we understand their paths. Occasionally, a brief streak crosses the sky. A meteor, a small fragment of rock burning in the atmosphere. It lasts seconds. Then darkness returns. The night sky feels quiet, but it is active. Light is traveling constantly, across enormous distances. The light from some stars began its journey before you were born, before your grandparents were born. In some cases, before recorded history. When you look at a star, you are seeing the past, not the present state of that star. This is not dramatic. It is simply how light works. Light has a speed, finite. It takes time to cross distance. So the sky is a record, a layered record of different moments. The darkness between stars may seem empty, but even that darkness holds faint light, too dim for the eye. With instruments, more detail appears. But for now, we remain with what the eye sees. A dome of black, dotted with light. Calm, repeating each night. Humans have looked at this same sky for tens of thousands of years. The same stars, the same slow rotation. Civilizations rose beneath it and passed. The sky remained. When we ask whether space ever ends, we begin here, with what we can directly see. Points of light, vast darkness, a sense of depth that is difficult to measure with the eye alone. This simple view is our starting point. From this quiet observation, we can begin to define what we mean by space itself. In the previous section, we looked at the night sky as it appears to the eye. Now we move one step deeper. We ask a simple question. What do we mean by space? The word sounds familiar. It feels obvious, but it is not precise. When people say space, they often mean the region beyond Earth's atmosphere. A place where there is no air, no clouds, no weather. That is a useful starting point. Earth is wrapped in a thin layer of gas, We call it the atmosphere. It extends upward for hundreds of kilometers. It becomes thinner with height. There is no sharp boundary, no solid line in the sky. Instead, the air slowly fades. At some point, it becomes so thin that we call the region beyond it space. This region is often defined near 100 kilometers above sea level. This boundary is practical, not physical. Beyond this height, aircraft cannot fly in the usual way. Wings need air. Rockets do not. So, in a simple sense, space begins where air becomes negligible. But this is only the local definition. It describes space near Earth, not space as a whole. When scientists use the word space, they often mean something broader. They mean the three-dimensional arena in which all physical objects exist. The distance between objects. The extension in all directions. Space is not an object. It is not a substance in the ordinary sense. It is the framework within which objects have position and separation. If you hold two stones apart, the gap between them is space. If you stretch your arms wide, the room between them is space. Scale does not change the concept, only the size. In everyday life, space feels empty. But even a room that appears empty contains air. Molecules move through it constantly. True emptiness is rare. In outer space, the density of matter is extremely low. There are still particles, stray atoms, radiation. But compared to Earth's atmosphere, it is close to a vacuum. A vacuum does not mean absolute nothing. It means very little matter. This distinction matters because when we imagine space, we often imagine pure nothingness, a kind of blank void. In reality, space has properties. It allows light to travel. It allows gravity to act across distance. It has measurable geometry. Modern physics treats space as dynamic, not passive. In classical thinking, space was like a stage. Events happened upon it. But the stage itself did not change. In modern cosmology, this view shifted. Space can expand. Space can curve. Space can stretch. This idea takes time to settle. We are used to thinking of distance as fixed. A meter remains a meter. But on cosmic scales, the distance between galaxies can increase over time. Not because they move through space in the usual sense, but because space itself expands between them. This means space is not merely emptiness. It participates in cosmic evolution. Still, we stay with the basics for now. Space is extension. Space is distance. Space is the possibility of separation. Without space, objects would have no where. There would be no here or there, no near or far. This leads to another quiet idea. Space and time are linked and is less than has hon. Zero hash is greater than. We often treat them separately. But physics combines them into space-time. Every event has a position in space and a moment in time. They are woven together. For now, we focus on the spatial part, the dimension of extension. When you look upward at the night sky, you are not seeing a ceiling. You are seeing through layers of increasing distance. First, the nearby atmosphere. Then, the region around Earth. Then, the wider solar system. Then, interstellar space. And beyond that, intergalactic space. Each layer is still space, just at a different scale. It does not change its basic nature. It remains extension. It remains distance. It remains the possibility for objects to be apart. Another clarification is helpful. Space is not the same as the objects within it. Stars are not space. Planets are not space. Gas clouds are not space. They occupy space. They shape space through gravity. But they are distinct from it. This distinction becomes important when we ask whether space ends. Because we are not asking whether stars end. We are asking whether the framework itself has a boundary. Before we reach that question, we ground ourselves again. Space near Earth feels empty, but it is structured by gravity. Earth pulls on the moon. The sun pulls on Earth. These pulls operate across space. Space allows interaction at distance. Light from the sun crosses space to reach us. It takes about 8 minutes. This time, delay is small by cosmic standards. But it reminds us that space has measurable size. It is not an abstract idea only. It has dimension. It can be measured in meters, in kilometers, in light years. A light year is the distance light travels in 1 year. This unit exists because cosmic distances are immense. Ordinary units become too small. As we move outward from Earth, distances increase quickly. The moon is hundreds of thousands of kilometers away. The sun is about 150 million kilometers away. The nearest star beyond the sun is over 4 light years away. Each step outward expands the scale dramatically. Yet all of it remains space. Continuous. Unbroken. There is no visible seam. No edge in sight. At least not locally. So when we use the word space, we mean the vast, three-dimensional expanse in which matter and energy exist. It is nearly empty in many regions, but not entirely empty. It has measurable geometry. It can expand. It can curve. And it extends far beyond what the eye alone can see. To understand how far it extends, we begin close to home and move outward through our own cosmic neighborhood. We now begin close to home. Not with distant galaxies, not with the edge of the universe, but with our own neighborhood, the solar system. The solar system is centered on the Sunday. The Sun holds most of the mass, most of the gravity. Everything here orbits it. 8 major planets circle the Sunday. Small rocky worlds near the center. Larger gas giants farther out. Between these planets is space. Wide regions of mostly empty distance. The planets are not close together. They only appear so in diagrams. In reality, the gaps are vast. If the Sun were the size of a large ball in a city park, Earth would be a small bead many meters away. The outer planets would be hundreds of meters distant. The space between them would feel empty. This emptiness is typical. Space is mostly separation, not clusters. Beyond the planets lies the asteroid belt. Many imagine it as crowded. It is not. The asteroids are far apart. Space still dominates. Farther outward are the gas giants. Jupiter, Saturn, Uranus, Neptune. Their orbits stretch across billions of kilometers. Yet even here, space is mostly quiet. Past Neptune, we reach the Kuiper Belt, a region of icy bodies, dwarf planets, frozen remnants from early formation. This belt extends far beyond the orbit of Neptune. Still, it is sparse. Still mostly empty. Then we move even farther. We enter a region known as the Oort cloud. This is not directly observed in full detail. It is inferred from long-period comets. The Oort cloud may extend halfway to the nearest star. That is an enormous distance, thousands of times farther than Neptune. And still, it belongs to the Sunday. Its objects remain loosely bound by solar gravity. Beyond this cloud, something changes. The Sun's influence fades. Gravity weakens with distance. Eventually, the pull of other stars becomes comparable. This is where interstellar space begins. Interstellar space means the space between stars, not between planets, not within one star system, but between separate suns. The distance to the nearest star is over 4 light years. Light takes more than 4 years to cross that gap. A spacecraft would take tens of thousands of years with current technology. This gap is mostly empty. Not perfectly empty. There are scattered atoms, thin gas, magnetic fields, but compared to planetary distances, it is vast. Our Sun is one star among many. The Milky Way galaxy contains hundreds of billions of stars, each separated by interstellar space. These stars are not arranged in neat lines. They orbit the galactic center, slowly, over millions of years. The galaxy itself has structure. A central bulge, spiral arms, a thin disk. We live in one of the spiral arms, not at the center, not at the edge, is less than hashon. Zero hash is greater than somewhere in between. Even within the galaxy, space dominates. Stars rarely collide. They are too far apart. The galaxy appears dense in photographs. But this is a compression of scale. In reality, each star is separated by trillions of kilometers. Between stars are clouds of gas, regions of dust, areas where new stars form. Yet even these clouds are thin by earthly standards. If you could stand within one, you might barely notice it. Now we widen the view. The Milky Way is not alone. It has neighboring galaxies, some small, some large. The nearest large galaxy is Andromeda. It lies more than 2 million light-years away. That distance is hard to picture. Light traveling at its maximum speed needs over 2 million years to arrive. Between our galaxy and Andromeda is intergalactic space, even emptier than interstellar space. Fewer atoms per cubic meter, greater stretches of quiet distance. Galaxies gather into groups. Groups gather into clusters. Clusters gather into superclusters. At each level, space remains the dominant feature. Matter forms nodes, filaments, web-like structures. But the majority of volume is empty. This pattern repeats. Objects separated by vast extension. Gravity linking them across distance. So when we ask whether space ends, we must notice something first. At every scale so far, space continues. From Earth orbit to the outer planets. From the Oort cloud to neighboring stars. From one galaxy to the next. We do not encounter a wall. We do not encounter a boundary. Only increasing distance, increasing scale, and increasing emptiness. This does not yet answer whether space is infinite. It simply shows that locally it appears continuous. The solar system has an outer region, but beyond it lies more space. The galaxy has a rough edge of stars, but beyond that lies more space. Each boundary of matter reveals further extension. So our journey outward has not found an end. Only transitions from one structure to another. From planetary system to stellar neighborhood. From galaxy to intergalactic expanse. To go farther, we must consider not just nearby regions, but the largest scale we can observe at all. We have moved from Earth to the solar system, from the solar system to nearby stars, from stars to galaxies. Now we widen the scale again. We consider the observable universe. This phrase has a specific meaning. It does not mean all that exists. It means all that we can currently see. Light travels at a finite speed, about 300,000 kilometers per second. Fast, but not infinite. Because light has a speed, it takes time to cross distance. When we look far away, we look into the past. This is a simple rule. Greater distance means older light. The universe itself has a finite age, about 13.8 billion years. That number sets a limit. Light from regions farther than a certain distance has not had enough time to reach us. This creates a horizon. Not a wall, not an edge of matter, but a limit to observation. We call this the observable universe. It is centered on us, not because we are special, but because observation always begins from a location. Any observer anywhere would see a similar horizon around themselves. The observable universe extends roughly 46 billion light-years in every direction. This number is larger than 13.8 billion. Because space itself has expanded while light was traveling. Expansion stretches distances. So the present-day separation is greater than the simple travel time might suggest. Within this sphere lie hundreds of billions of galaxies, each containing billions of stars. The scale becomes difficult to picture. So we return to structure. On the largest scales, galaxies are not scattered randomly. They form a pattern known as the cosmic web. Long filaments of galaxies stretch across space. These filaments intersect at dense clusters. Between them lie vast voids, regions with very few galaxies. The universe at large scale resembles a network. Dense threads, wide gaps. Again, space dominates volume. Even where galaxies gather, emptiness surrounds them. When we observe distant galaxies, we see them as they were billions of years ago. Some appear young, compact, active. Others appear mature, more structured. The farther we look, the earlier the universe appears. Eventually, galaxies become faint and harder to distinguish. We approach a deeper boundary. This boundary is not made of stars. It is made of radiation, the cosmic microwave background. This radiation comes from a time about 380,000 years after the beginning of cosmic expansion. Before that time, the universe was opaque. Light could not travel freely. After that time, atoms formed. The universe became transparent. The light released then still fills space today. It has stretched into microwave wavelengths due to expansion. This radiation marks the farthest light we can currently detect. It forms a kind of observational boundary. Beyond it, we cannot see with light. Not because nothing exists, but because earlier light cannot reach us in its original form. So the observable universe has layers. Nearby galaxies, distant galaxies, early galaxies, and finally, background radiation. Each layer represents deeper time, deeper distance. This observable region is vast. Yet, it may not be the whole universe. The horizon is defined by light travel time, not by a physical edge of space. If the universe extends beyond what we can see, those regions remain unobserved. They are not necessarily separate. They are simply beyond our current reach. This distinction is important. Observable does not mean total. It means accessible by light. As time passes, the observable universe changes. Light from slightly farther regions has more time to arrive. The horizon shifts slowly, but expansion also stretches space. Some regions recede faster than light can bridge, not because they move through space too quickly, but because space itself expands between us. This creates a subtle effect. Some galaxies visible today will eventually fade beyond reach. Their light will never again arrive. The observable universe is dynamic, not fixed. Still, at this moment, we can describe its approximate size. A sphere around us. Tens of billions of light years in radius. Filled with structure, yet mostly empty. When we imagine standing at its boundary, we must be careful. There is no physical shell there. No curtain. No abrupt drop into nothingness. The boundary is informational. It marks the limit of received light. If you were located billions of light years away, your observable universe would be centered on you. You would see a similar sphere, with different galaxies inside, but the same general structure. This symmetry suggests something calm and steady. On large scales, the universe appears uniform, not identical in every detail, but statistically similar. This uniformity supports modern cosmology. It allows models of expansion and evolution. So at this scale, we have reached a limit. Not the end of space, but the end of what we can currently observe with light. Beyond that horizon, space may continue. It may be much larger. It may even be infinite. We do not yet know. But to approach that question, we must now examine how space itself behaves on cosmic scales. We have described the observable universe, its size, its horizon, its large-scale structure. Now we turn to a deeper question. How does space behave? Not what it contains, but how it changes. In the early 20th century, astronomers noticed something steady. Distant galaxies show redshift. Their light is stretched toward longer wavelengths. The farther the galaxy, the greater the redshift. This pattern is consistent. It suggests expansion. Not expansion into something, but expansion of space itself. This idea requires patience. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move apart. Not because they slide across the surface, but because the surface stretches. Each dot sees the others receding, is less than Hashone. Zero hash is greater than. No dot sits at the center of the surface. The expansion happens everywhere. This analogy is limited. The balloon has an outside. The universe does not require one. The point is simpler. Distance between galaxies increases over time. Measurements support this. The rate of expansion is described by the Hubble constant. Its value is refined over time. But the trend remains. Space expands. This expansion began in a hot, dense state, often called the Big Bang. The term can be misleading. It was not an explosion into empty space. It was the rapid expansion of space itself. Everywhere at once. Early on, the universe was smaller, denser, hotter. As space expanded, it cooled. Matter formed. Structures developed. Galaxies emerged. The expansion continues today. It is not slowing to a stop. In fact, evidence suggests it is accelerating. This acceleration is linked to dark energy. Dark energy is a name for an observed effect. It represents the tendency of space to expand faster over time. Its precise nature remains uncertain. But its influence appears consistent across observations. So space is not static. It changes with time. This leads to a calm but important realization. The size of the universe depends on when you measure it. Earlier epochs had smaller separations between galaxies. Future epochs will have larger separations. Expansion does not mean local objects stretch. At small scales, gravity holds systems together. Galaxies remain intact. Solar systems remain stable. Expansion dominates only at vast distances. So space behaves differently at different scales. Locally stable, cosmically dynamic. Now we consider geometry. Space may have curvature. Curvature does not require visible bending. It refers to how parallel lines behave over large distances. In flat geometry, parallel lines never meet. In positively curved geometry, they may converge. In negatively curved geometry, they diverge. Observations suggest that on large scales, space is very close to flat. Not perfectly confirmed, but consistent within measurement limits. A flat universe can still be finite or infinite. Flatness does not settle that question. It only describes local geometry. If space is finite, it may curve back on itself, like the surface of a sphere in higher dimensions. In that case, traveling far enough in one direction could eventually bring you back to your starting point. Not because of a boundary, but because of curvature. If space is infinite, it extends without bound. No wrapping, no closure. Current evidence does not rule out either possibility entirely. Measurements constrain curvature tightly. They suggest near flatness. But near flat can still hide large-scale structure beyond observation. Another concept enters here. Inflation. Inflation refers to a brief period of extremely rapid expansion early in cosmic history. It helps explain uniformity across large regions. It smooths curvature. It stretches space dramatically. If inflation occurred as models suggest, the universe may be vastly larger than the observable portion, possibly far beyond our horizon. This does not add drama. It adds scale, quiet scale. So space expands. Space may curve. Space evolves with time. These behaviors shape the question of an edge. Because if space expands everywhere, there is no preferred center. If geometry is smooth, there may be no sharp boundary. The idea of an edge may come from everyday experience. Rooms have walls. Fields have fences. But space at cosmic scale may not behave like enclosed land. It may behave like geometry itself. A structure without edges in the ordinary sense. With this understanding of expansion and geometry, we are ready to examine directly whether the universe has a physical boundary or whether the concept of an edge may be misleading. We now arrive at a direct question. Does the universe have a physical edge? Not a horizon of observation, not a limit of light, but a boundary in space itself. When we imagine an edge, we picture something familiar. A wall, a cliff, a border. These images come from daily life. Rooms end at walls. Oceans meet shorelines. Land meets sky. But these examples share a property. They exist inside a larger space. A wall separates one room from another. A shoreline separates land from sea. An edge implies something beyond it. So, if space had an edge, we must ask, what lies beyond that edge? If the answer is nothing, we must define what nothing means. If the answer is more space, then the edge was not an edge at all. This shows the difficulty. The concept of an edge may not apply easily to space as a whole. Let us examine the finite case first. Suppose the universe is finite in size. Finite does not automatically mean bounded by a wall. Consider the surface of a sphere. It has a finite area. You can measure it. Yet, it has no edge. You can travel in one direction indefinitely. You will not encounter a boundary. Eventually, you return to where you began. The surface curves back on itself. This is a two-dimensional example. Our universe has 3 spatial dimensions. But the principle can extend. A 3-dimensional space could curve in a higher dimension. It could be finite without edges. In such a universe, there would be no wall at the boundary. No final barrier. Just continuous geometry. The idea feels unfamiliar. Because we rarely encounter closed spaces without edges in daily life. Yet mathematically, such spaces are consistent. Observations of cosmic curvature help test this possibility. Measurements of the cosmic microwave background suggest near flatness. Very small curvature. Within current limits, the universe appears flat. A perfectly flat universe could still be finite. If it wraps around in a more complex topology. Or it could be infinite. Extending without bound. Both options remain consistent with data. Now consider the infinite case. Infinite space has no boundary. It does not curve back. It does not close. It simply continues. In every direction. Without end. This idea also challenges intuition. We are accustomed to limits. Even large things have edges. But infinity is not a large number. It is the absence of limit. In an infinite universe, there is no special center. Every point is surrounded by more space. The large-scale structure could repeat statistically. Not identically, but with similar patterns. Galaxies, voids, filaments, over and over. The observable universe would then be a small region within something much larger. Perhaps vastly larger. We would never see the whole. Only our portion. It is important to remain steady here. Infinite does not imply chaotic. It does not imply mystical. It is simply a geometric property. Is less than hashone. Zero hash is greater than a statement about extent. There is another subtle point. The universe can be finite in age, but infinite in spatial extent. Expansion describes how distances change over time. It does not automatically define total size. If space began expanding everywhere at once, it could have been infinite from the start. Just denser. Just hotter. The Big Bang does not require a central point in pre-existing emptiness. It describes a state of high density across all space. This distinction is quiet but important. It removes the need for an outer shell. It removes the need for a surrounding void. Space may simply be the totality of spatial relations. Nothing outside. Nothing enclosing. Just geometry itself. When people ask what lies beyond the universe, the question may be misframed. If the universe includes all space, then beyond space is not a location. Location requires space. Without space, the concept of beyond loses meaning. This is not an attempt to avoid the question. It is a clarification of terms. An edge implies contrast. Inside versus outside. But if space is the entire spatial framework, outside may not exist in a spatial sense. There could be other structures, other regions with different physical properties. But they would require their own spatial description. At that point, we are no longer speaking of beyond space. We are expanding the definition of space. So the simplest models suggest two broad options: finite without edge, or infinite without boundary. Neither includes a hard wall. Neither predicts a cliff at the end of distance. This does not close the discussion. It narrows it. It shifts the focus from physical barriers to geometry and topology. The question becomes less about hitting an edge and more about the shape of space. To explore further, we must consider what may lie beyond the observable region and how inflation and broader cosmological models extend the picture beyond what we can directly measure. We now move beyond the idea of a single expanding universe. We consider a broader possibility, not as speculation for its own sake, but as an extension of established models. The concept is simple in structure. It asks whether our observable universe is one region among many. This idea emerges naturally from inflation. Inflation describes a rapid expansion in the early universe, a brief but intense growth of space. It smooths irregularities. It explains large-scale uniformity. It aligns with observations of the cosmic microwave background. Yet some versions of inflation do not stop everywhere at once. In certain models, inflation continues in some regions, while ending in others. Where it ends, a universe like ours forms. Where it continues, space keeps expanding rapidly. This leads to what is sometimes called eternal inflation. The term sounds dramatic, but the structure is mathematical. Space expands at different rates in different regions. Local pockets settle into slower expansion. Those pockets become universes. Each pocket is vast, possibly infinite. Each may have slightly different physical constants. Small variations in energy fields could lead to different outcomes. Different particle masses, different strengths of forces, different structures. This collection of regions is often called the multiverse. The word can mislead. It suggests separate bubbles floating in emptiness. But the emptiness itself would still be space. Expanding. Dynamic. The broader structure would not sit inside something else. It would be the full extent of spacetime described by the inflationary model. Our observable universe would be one region within that larger framework. We would not see the boundary between regions. The distances would be too great. Expansion would separate them faster than light can travel between them. So observational access becomes limited. Not by a wall, but by expansion itself. There is another path to similar ideas. It comes from quantum mechanics. Some interpretations of quantum theory suggest that all possible outcomes occur, not in sequence, but in branching structures. This is sometimes called the many worlds interpretation. This is less than ℏ. Zero hash is greater than. In this view, quantum events do not select a single outcome. Instead, reality branches. Each branch contains a consistent history. These branches do not interact after separation. They are part of a larger quantum state. This concept differs from inflationary multiverses. One arises from cosmology, the other from quantum foundations. Yet both challenge the assumption of a single, isolated universe. It is important to remain precise. These ideas are theoretical. They arise from extending equations that already describe observed phenomena. Inflation has observational support. Quantum mechanics has strong experimental validation. The multiverse concepts come from extrapolating those frameworks. Direct evidence for other universes does not currently exist. This does not invalidate the models, but it limits certainty. Science proceeds carefully here. Hypotheses remain open. Some physicists explore string theory landscapes. String theory allows many possible vacuum states. Each state corresponds to different physical constants. The number of possible configurations is large, extremely large. In such a landscape, different regions of space could settle into different minima. Each minimum would define a universe with its own laws. Again, the mechanism resembles inflationary separation. Regions become causally disconnected. They cannot exchange information. From our perspective, they are unreachable. Yet mathematically, they belong to the same overarching structure. The idea of many universes can feel expansive, but the reasoning remains grounded in equations. Fields fluctuate. Symmetries break. Regions evolve differently. The repetition of this pattern is calm. Variation emerges from uniform rules. Just as galaxies formed from small fluctuations. Just as stars formed within galaxies. Structure builds from underlying laws. The multiverse, if real, would follow the same principle. There is also a philosophical dimension. If many universes exist with different constants, we may ask why ours permits complexity. Why stable atoms form? Why long-lived stars shine? One approach is selection. Observers arise only in regions compatible with structure. This is sometimes called the anthropic principle. It does not claim purpose. It describes conditional probability. We observe conditions consistent with our existence, because otherwise we would not be here to observe. This reasoning is careful. It avoids exaggeration. It frames observation as part of the system. Still, caution is necessary. The multiverse remains difficult to test directly. Some researchers search for indirect signatures, possible imprints in the cosmic microwave background, patterns from bubble collisions. So far, no confirmed evidence has appeared. The absence of detection does not end the inquiry, but it tempers conclusions. Scientific models must remain connected to observation, even when exploring large scales. Whether or not multiple universes exist, one principle remains steady. Our observable region has limits defined by light and time. Beyond that horizon, structure may continue. Perhaps uniformly, perhaps variably. The distinction between observable and total becomes central. We must separate what we can measure from what theory allows. This separation is not a weakness. It is clarity. Knowledge grows from defined boundaries, even if those boundaries shift with time. The question of many universes ultimately reflects a deeper theme. The scale of reality may exceed our immediate perception. Just as Earth is not the center of the solar system, Just as the solar system is not the center of the galaxy, expansion of perspective has occurred before. Each step required evidence. Each step required patience. The multiverse, if confirmed, would represent another widening. If not confirmed, the investigation still refines our models. Either outcome contributes to understanding. For now, we stand within one observable universe. We measure its expansion. We map its structure. We study its background radiation. We test its physical laws with increasing precision. The larger framework remains an open question. A question approached with equations rather than imagination alone. A question shaped by data and by restraint. From here, it becomes natural to examine how our understanding of space connects to time itself and how the structure of spacetime shapes the ultimate fate of everything we observe. We now turn to time. Not as a clock on a wall, not as a schedule, but as a dimension woven together with space. Modern physics does not treat space and time as separate backgrounds. It treats them as a single structure. This structure is called spacetime. The term is simple. The meaning is precise. In classical thinking, space is a stage. Time flows independently. Events happen within both, but they do not influence the stage itself. This view changes with relativity. According to general relativity, mass and energy shape spacetime. Spacetime is not rigid. It curves. That curvature guides motion. Planets follow curved paths, not because of invisible forces alone, but because the geometry around massive bodies is altered. Gravity becomes geometry. This insight is steady. It replaces force with structure. It replaces attraction with curvature. Objects move along the straightest possible paths in curved spacetime. These paths are called geodesics. The mathematics is detailed. The concept is calm. Matter tells spacetime how to curve. Spacetime tells matter how to move. Time itself is affected by gravity. Clocks run at different rates in different gravitational fields. A clock near a massive object ticks more slowly. This effect is measurable. It is not abstract. Satellites in orbit must correct for it. Without correction, navigation systems would drift. Time is therefore not universal in the simple sense. It is local. It depends on motion and gravity. This leads to a broader view of cosmic time. In cosmology, we define time using the expansion of the universe. We speak of cosmic time. It measures duration since the early hot state. This clock is shared by observers who move with the general expansion. It provides a common reference. Yet even here, precision matters. local variations exist. Galaxies cluster, structures form, gravity shapes regions differently. When we project forward in time, we ask about the fate of expansion. Observations show that expansion is accelerating. Distant galaxies recede at increasing rates. This acceleration is attributed to dark energy. The term is descriptive. Its nature remains uncertain. Dark energy behaves like a property of space itself. As space expands, more of it appears. The energy density remains nearly constant. So the total effect grows with volume. Expansion feeds on expansion. If acceleration continues, distant galaxies will move beyond our observable horizon. Light emitted in the far future will never reach us. The observable universe will gradually empty, not because matter disappears, but because separation increases. Over immense timescales, stars will exhaust their fuel. Stellar formation will slow. Eventually, it will cease. Existing stars will fade. Remnants will remain. White dwarfs, neutron stars, black holes. Black holes themselves are not eternal. Through quantum processes, they emit radiation. Very slowly. Over extreme durations, they lose mass. They evaporate. The timescales exceed ordinary comprehension. Yet the equations remain consistent. If this scenario holds, the universe approaches a state of increasing entropy. Energy spreads. Temperature differences decline. This is sometimes called heat death. The phrase sounds dramatic. The principle is thermodynamic. Entropy measures the number of microscopic configurations consistent with a macroscopic state. Systems evolve toward higher entropy, not by intention, but by probability. The early universe had low entropy relative to its energy density. Structure formation increased entropy while creating order locally. This duality is subtle. Galaxies form. Stars shine. Life emerges. Yet overall entropy increases. The arrow of time aligns with this growth. We remember the past, not the future, because entropy was lower then. The connection between space-time and entropy remains an active area of research. Black hole thermodynamics suggests deep links. Event horizons possess entropy proportional to area. Information may be encoded on boundaries. These ideas hint that space-time itself could have microscopic structure, not continuous at the smallest scales, perhaps emergent from deeper principles. Quantum gravity seeks to clarify this. If space-time has a quantum description, time may not be fundamental in the way we perceive it. Some equations describing the universe do not contain explicit time parameters. Instead, time may arise from relationships between changing quantities. This perspective is careful. It does not remove time from experience. It questions its basic status in fundamental law. The inquiry remains open. There are alternative long-term possibilities. If dark energy changes over time, expansion could slow. It could reverse. A contraction might follow, leading to a high-density state again. This is sometimes called a big crunch. Current data favor continued acceleration, but measurement continues. Precision improves gradually. Throughout these projections, one theme persists. Space-time evolves. Geometry changes. Distances grow. Structures transform. The universe is not static. It is dynamic on every scale. Yet the laws governing that change show consistency. Equations derived a century ago still describe gravitational waves observed today. Observations refine constants. They do not overturn coherence. Our understanding of space led to geometry. Geometry led to curvature. Curvature led to expansion. Expansion leads to questions of fate. Each step follows from the previous one. Calmly, incrementally. We do not step outside the system. We model it from within, using measurement, using mathematics. As we continue, it becomes necessary to reflect on the limits of knowledge itself and on how observation, theory, and uncertainty shape the boundaries of what we can truly claim to understand. We now turn to the limits of knowledge. Not as a defeat, not as a barrier, but as a structural feature of inquiry. Every measurement has range. Every theory has domain. Understanding grows within constraints. The observable universe defines one clear limit. Light travels at a finite speed. The universe has a finite age. Therefore, we can only receive information from a finite distance. Beyond that distance, events may occur. But their light has not reached us. This is not a technological limitation. It is geometric. Expansion stretches space. Some regions recede too quickly for signals to bridge the gap. This horizon defines what can be observed. There is also a limit in resolution. We cannot see arbitrarily small scales directly. Probing shorter distances requires higher energies. Particle accelerators extend this reach. But practical limits exist. Energy, cost, and engineering constrain experiment. At extremely small scales, quantum effects dominate. Classical geometry no longer applies. A full theory of quantum gravity remains incomplete. So our picture of spacetime at the smallest scale is provisional. There are conceptual limits as well. Measurement disturbs quantum systems. Uncertainty is not a flaw in instruments. It is built into the structure of physical law. Position and momentum cannot both be known exactly. Precision in one reduces precision in the other. This principle is formal. It is experimentally verified. Knowledge at microscopic scales is probabilistic. Outcomes are described by distributions, not single certainties. Cosmology adds further layers. We observe the universe from one location, one time. We infer large-scale properties by assuming uniformity. This assumption is supported by data. Yet it remains an assumption about scales beyond direct sampling. We cannot step outside the universe to view it as a whole. All models are constructed from within. This embedded perspective shapes interpretation. There are also statistical limits. The cosmic microwave background provides a snapshot of early fluctuations. But we have only one sky to measure. Large-scale variations are subject to cosmic variance. Some uncertainties cannot be reduced by better instruments. They arise because we observe one realization of possible fluctuations. The sample size of universes available to us is one. This shapes confidence intervals. Theory itself has boundaries. Mathematical consistency does not guarantee physical realization. Many equations can be written. Fewer correspond to nature. Experimental test remains central. When direct tests are unavailable, indirect consistency becomes important. Predictions must align with known phenomena. Otherwise, revision follows. This cycle repeats. Uncertainty does not imply ignorance in total. It defines ranges. Parameters are estimated with error bars. Those bars shrink with improved measurement. Over decades, cosmological parameters have become more precise. The expansion rate is constrained within narrow margins. Matter density is quantified. Dark energy fraction is estimated. Yet, small tensions remain. Different measurement methods yield slightly different values. These discrepancies motivate refinement. At a deeper level, we confront epistemic humility. Our cognitive tools evolved for survival on a planet, not for grasping curved spacetime. Mathematics extends intuition. Instruments extend senses. Collaboration extends individual capacity. Still, models are representations. They map structure. They do not become the structure itself. Recognizing this prevents overstatement. There are questions that may remain undecidable. If regions beyond our horizon differ fundamentally, we may never confirm it. If spacetime has features beyond observational reach, inference may stop at consistency. Some propositions may be empirically equivalent, distinguishable in mathematics, indistinguishable in measurement. In such cases, preference may rely on simplicity or coherence, not on direct verification. Yet history shows progress within limits. The size of the Milky Way was once unknown. The existence of other galaxies was debated. The expansion of the universe was unexpected. Each boundary shifted with evidence. Instruments improved. Theory sharpened. Data accumulated. Limits did not vanish. They moved outward. The practice of science, therefore, balances ambition and restraint. It asks large questions. It accepts partial answers. It quantifies doubt. It refines statements. Confidence is graded, not absolute. Claims are provisional, not arbitrary. In cosmology, this balance is especially visible. We speak of models, of best fits, of likelihoods. We distinguish observation from extrapolation. We separate measurement from interpretation. Is less than has known. Zero hash is greater than. This structure provides clarity. It prevents confusion between data and narrative. As we stand within these limits, one realization becomes steady. The universe is accessible in part, not in full. Our knowledge is layered. Some layers are firm. Some are developing. Some remain speculative. The distinction among them is essential. From this perspective, the question shifts slightly. Not only what is the universe, but how do we responsibly speak about it? How do we frame certainty? How do we communicate uncertainty? These questions lead naturally to a final reflection on perspective itself and on how human understanding fits within the vast structure it seeks to describe. We arrive now at perspective. Not the perspective of instruments alone, not the perspective of equations alone, but the perspective of observers within the system they study. Human understanding operates from inside the universe. We do not stand outside it. We do not view it from a distance. All knowledge is gathered locally. We began with the night sky, points of light, patterns, motion. From those observations, models formed. From models, predictions followed. From predictions, tests were designed. Over time, a structure of understanding emerged. Not complete, but coherent. We learned that Earth is not central. The solar system is not central. The galaxy is not central. Even our observable universe may not be unique. Each step reduced assumed privilege. Each step expanded scale. This pattern is steady. Yet there is another side. Though not central, we are not irrelevant. The universe is understood through conscious inquiry. Measurement requires intention. Interpretation requires reasoning. The laws of physics describe processes, but explanation arises in minds. This is not a mystical claim. It is an acknowledgement of participation. Our species occupies a narrow band of scale between the quantum and the cosmic. We cannot see atoms unaided. We cannot see galaxies with the naked eye beyond a few. Instruments extend both directions. Mathematics connects them. Patterns repeat across scale. Structure forms from simple rules. Complexity emerges gradually. The universe does not present itself all at once. It reveals layers. Background radiation reveals early conditions. Galaxy surveys reveal structure. Particle experiments reveal interactions. Each layer refines the previous one. Contradictions prompt revision. Agreement strengthens confidence. We have seen that space may be finite without edge, or infinite without boundary. That expansion shapes what we observe. That time is interwoven with geometry. That entropy gives direction to change. That horizons limit visibility. That uncertainty limits precision. These are not failures. They are structural truths. The practice of cosmology, therefore, rests on balance. Curiosity guided by evidence. Imagination guided by mathematics. Ambition guided by restraint. We ask large questions. We accept measured answers. We distinguish between what is known, what is inferred, and what is proposed. Perspective also reshapes daily experience. The ground beneath us is part of a rotating planet. The planet orbits a star. The star moves within a galaxy. The galaxy drifts within expanding space. None of this disrupts ordinary life. Yet it quietly reframes it. Local events occur within vast structure. The scales differ. The laws connect them. We do not need dramatic language to appreciate this. The facts themselves are sufficient. A universe governed by consistent laws, structured by geometry, evolving over billions of years, capable of forming matter, stars, planets, and observers. This description stands without embellishment. There will always remain unanswered questions. What preceded the earliest measurable state? Whether constants vary beyond our horizon? How quantum gravity completes the picture? These questions remain open. Openness is not instability. It is space for continued inquiry. In the end, perspective returns us to scale and method. We are small relative to cosmic distances, yet capable of mapping them. We are brief relative to cosmic time, yet capable of reconstructing it. This dual fact defines our place. The universe does not adjust itself to human expectation. We adjust our models to the universe. When evidence shifts, theory shifts. When precision improves, parameters narrow. The process continues. With this, the structure of our exploration feels complete. From the visible sky to the curvature of spacetime. From expansion to entropy. From horizons to humility. Each section connects. Each builds on the previous one. The picture remains provisional, yet stable in outline. We conclude not with certainty about every detail, but with confidence in method, observation, measurement, mathematical structure, careful revision. These tools remain reliable. The universe extends beyond what we see. Yet what we see is enough to reveal its coherence, enough to trace its history, enough to frame its possible futures. And within that understanding, we find a steady orientation. Closing reflection begins now. We have looked outward across distance. We have looked backward across time. We have examined structure, limit, and law. The result is not spectacle. It is clarity. A quiet map of reality as best we can draw it. The stars above remain points of light, but we now understand them as suns, as systems, as parts of galaxies moving through expanding space. The ground beneath remains solid. Yet we know it travels through space-time shaped by gravity. Nothing in this understanding requires exaggeration. The scale is large. The laws are consistent. The method is steady. We remain observers within the universe, learning gradually, correcting carefully. The exploration continues, quietly, methodically, and that is enough.